Okay, so our last speaker will be Anne-Caroline Bronzi from Universidade Federal do Rio de Janeiro. And she's going to talk about on the convergence of a statistical solution of the 3D Navier-Stokes alpha model as alpha tends to 0.
Okay, thank you. First of all, I would like to thank the organizers for the opportunity of presenting my work here. And this is joint work with Ricardo Rosa. He gave a talk yesterday about something similar with what I'm going to talk today. So let me start with the equations considered in this work. So the first one is the 3D Navier-Stokes equations with periodic boundary condition, just to simplify. So U is the velocity field, F is the external force, nu is the viscosity, and P is the pressure. And the other equation that we are concerned with is the 3D Navier-Stokes alpha model with periodic boundary condition. And this is a regularized approximation of the Navier-Stokes equations in the sense that if we take alpha, if you take alpha equals to 0 here, we recover the Navier-Stokes equations. Okay. And so here V is the unknown variable, U is a smoothing of V, P is the pressure, F is the external force, and alpha is a positive constant. Actually, there are some physical properties of this equation, but I don't have time to talk about this. So just to fix the notation, H stands for the set of divergence-free vector fields, L2 vector fields, which satisfies the periodic boundary conditions with 0 average. V is a subset of H of the H1 vector fields. V prime is the dual of V, and D of A to the power S is the domain of powers of the Stokes operator for S, a real number. And when we write 8 with the subindex W, is because we want to emphasize that the topology considered is the weak one. When we don't put the W, it's because we are considered the strong topology. Okay. So let me start with this figure, which is a good picture of the idea behind the study of statistical solutions. So on the left-hand side, we have the instantaneous view of a jet in a cross-flow. So we can see that it's a quite irregular behavior and also unpredictable in the sense that if we look for a particle now, in a future time, we have no idea where it's going to be. Not no idea, but it's hard to predict. But on the right-hand side, we have the time average view of the flow, and it seems more regular, at least more predictable, and still contains the main information about the behavior of the flow. Okay. Okay. There are several manners of consider an average. So time average is one example, but there is a more general and actually more rigorous way to do this, which is consider a family of probability measures defined on the phase space of the Navier-Stokes equations. And for instance, if you wanted to consider the mean velocity, we just calculate this integral for this family of probability measures. And Foyaz and Prod introduced this notion of statistical solutions for the Navier-Stokes equation as the family of probability Borel measures, mu t, which satisfies this Liouville type equation, which is related with the Navier-Stokes equations, plus mean energy inequality, which I'm not going to write here because it's a lot of things, but it's related with the energy inequality of the weak solutions of the Navier-Stokes equations, plus regularity conditions, which is related with the space of the weak solutions. Okay, so Foyaz and Prod introduced this notion of statistical solutions. Then, some years later, Vishik-Fursikov gave a new notion of statistical solutions as a probability measure, now in the time-dependent trajectory space, which is not the most natural one for the weak solutions, but still it's a new notion, and some results was proved using this. And more recently, Foyaz, Rose, and Teman elaborated a new notion of statistical solutions with several good properties. The first one is that they can relate the notion due to Foyaz, Prod, and Vishik-Fursikov, and also with this notion, the problem is more tractable. Okay. And this new notion of statistical solutions, they also have this sense of probability measure in the time-dependent trajectory space, which is the more natural for the Leray-Hopf weak solutions. And the good property is that when we project this probability measure in the time, we gain a family of measures, which is a statistical solution in the sense of Foyaz Prod. Okay. And the result that I will present today is that statistical solutions of the 3D Navier-Stokes alpha model converge to statistical solutions of the 3D Navier-Stokes equation as alpha goes to 0. And the notion of statistical solution that we used here is exactly this one due to Foyaz, Rose, and Teman. Okay, so just the definition of Leray-Hopf weak solution. So first of all, here we have the functional formulation of the Navier-Stokes equation, which is just apply the Leray projector, which is the projection from L2 to the space of divergence free vector fields. And we say that U is a Leray-Hopf weak solution if it belongs to this space. Remember that here W stands for the weak topology, and satisfies the equation in this weak sense, in the sense of distributions, and satisfies the energy inequality. And finally, it's strongly continuous at the origin. Okay, in order to define the statistical solutions, we need to define the trajectory space. So the first one, U, is just the space of Leray-Hopf weak solutions, but this space has a problem, which is if we consider a sequence in this space, when we take, for instance, if we consider a convergent sequence in this space with the topology of uniform weak convergence on compact intervals, the limit may not belong to this space. Okay, so in some sense it's not closed. And so in order to deal with this issue, they defined this other space, U sharp, which is the set of Leray-Hopf weak solutions, which doesn't contain the orange. So here we don't ask the solution to be strongly continuous at the orange. And this is just a bounded set inside this trajectory space. So the Vishik-Fursikov measure is a Borel measure in the trajectory space. So here I borrowed the picture from Ricard's talk. And so it is a Vishik-Fursikov measure if it's carried by the trajectory space, Carried means that whole of the set has full measure, which is 1 in this case. Then also satisfies this boundedness of the mean energy and this type of continuity at the orange. And of course, they used this set in order to avoid problems. But at the end, actually, they proved that this measure is carried by the set of interest here. Okay, so it's just a technique in order to deal with this issue. Okay, and the statistical solutions will be the projection of these measures. Okay, so just to be more precise, here we have the projection operator, and a projection of a measure is defined by this formula, which is known. And we say that a Vishik-Fursikov statistical, we say that a family of probability measures is a Vishik-Fursikov statistical solution if it's a projection of a Vishik-Fursikov measure in each time t. So this is a picture. So remind that we had this hole in the trajectory space, and if we project in each time, we will obtain this family of measures in the phase space. And an important remark, an important result that actually I have already mentioned, is that every Vishik-Fursikov statistical solution is a statistical solution in the sense of Foyer's product. So here's the relation between them. And okay, so that was the definition for Navier-Stokes equations. Now we are going to do the same for the Navier-Stokes alpha model. So here we also have the natural functional formulation, but because of some technical details, actually it's better to consider an equivalent functional formulation, and here we follow the framework of Vishik and Chepskov, but it's equivalent. It's not a problem. And we have the definition of solution for the Navier-Stokes alpha model. So here we have the same space as the solution for the Navier-Stokes equations, with the exception of this one, which for the Navier-Stokes equation we had here the weak topology, now we have the strong topology. And also here we have the energy equality. Okay, while in the Navier-Stokes equation we had the energy inequality. So there is the result of well-posings for this equation, and also the convergence of the solutions of the Navier-Stokes alpha model for a solution, for a Leray-Hopf-Wick solution of the 3D Navier-Stokes equation. And as you can expect, this is going to play an important role in the proof of our result. Okay. So the trajectory space for the Navier-Stokes alpha model are simpler, because now we don't have the problem at the orange, because here we have the continuity, the stronger continuity. So we define the trajectory space as the set of solutions, and analogs to the Navier-Stokes equations, we define alpha Vishik-Fursikov measure as being a measure which satisfies these two conditions. The first one is to be carried by the trajectory space, and the second one is the boundedness of the mean energy. Okay, and now the functional setting. So now we have two trajectory space, and we need an ambient space which contains both of them. The natural space would be the space of weakly continuous vector fields, but this space also has a problem, which is if you consider a bounded subspace inside the space of weakly continuous function, this space is not compact, and at some point we will need this compactness. So in order to overcome this issue, actually we consider a subspace of the space of weakly continuous vector fields, adding we ask the vector fields to satisfy also the a priori estimates, which are the same for the Navier-Stokes equation and for the alpha Navier-Stokes equation, since we are considered that equivalent formulation for the alpha Navier-Stokes equation. So don't worry with this. We just have to keep in mind that epsilon is the ambient space, and this space here, epsilon of R, is a bounded space which is compact. So I summarized here. And another important property is that epsilon is a completely regular Hausdorff space. We are going to need this for the convergence of the measure, as we will see in a moment. And so the compactness here is important in order to obtain that this space is metrizable. And because this space is metrizable, we can consider a metric in this space, and then we can consider the distance between these two trajectory space. And because of the result of Vishik-Fursikov and Chepskov, the one which says which gives the convergence of solutions of the Navier-Stokes alpha model to a solution of the Navier-Stokes equations. Because of that result, we can conclude that the limit when alpha goes to 0 is 0. The distance between these two trajectory space goes to 0 as alpha goes to 0. And so we need just some definitions regarding the measures. So the first one is, which is a Borel. We say that a Borel measure is tight if it's inner regular with respect to compact sets. Okay. And we say that a sequence of Borel measures is uniformly tight if for every epsilon positive there exists a compact set such that the sequence satisfies this estimate uniformly in N. And the topology here is given by this type of convergence, which is the convergence in the sense of these integrals. It's in some sense the dual of the space of measures. And here we need this Topsoy's theorem, which is a generalization of Prohorov's theorem. Prohorov's theorem is when X is a metric space, and here we don't have this, okay? But we have that X, our ambient space is completely regular, Hausdorff space, and the theorem says that if you have this type of set, then every family of tight measure, which is uniformly tight, is relatively compact with respect to this convergence. So we have all we need to prove the theorem. So this is the result. Let μ0 be a Borel probability measure with finite mean energy, which means that this integral is finite. And consider a sequence of alpha and Vishik-Fursikov measure such that each element, the projection of each element at time t equals to 0 is this initial data, this is initial measure for all n. Then the conclusion is that we can extract a subsequence which converges to a Vishik-Fursikov measure. And moreover, the projected time t equals to 0 is the μ0. And we have the same result for the statistical solutions, which says that if you just consider the projection of these measures here, then we have alpha Vishik-Fursikov statistical solution, and the corresponding convergent sequence will converge to a Vishik-Fursikov statistical solutions, which is, as we already know, a Fourier-Sprott statistical solution. And the proof goes in the same line as the classical theory for individual solutions, which is we start with the initial data, let's say in an energy space, then we use the a priori estimate to conclude that the sequence is compact in some sense, and then we extract a subsequence and prove that the limit is a solution. The idea is the same, just that here we have to translate this for the measures. So here we have that our initial data is in the energy space. We have energy estimates. Then we can conclude that the sequence is uniformly tight. And because of this, we can use the Topsoy's theorem to conclude that we can extract a convergent subsequence which converts to a Borel probability measure. And then we have to prove that this measure is a Vishik-Fursikov measure. And to do that, we just use what we already have in hands, which is this that this the distance between these two trajectory space goes to 0, that rho alpha n is a alpha Vishik-Fursikov measure, and that we have this convergence. Then with this in hands, we can conclude that rho is carried by the trajectory space of the Navier-Stokes equations. And also using our hypothesis, we can conclude the other part of the definition of alpha Vishik-Fursikov measure. And I forgot to put here, but to obtain the convergence of the statistical solutions, we just use a change of variables, let's say in the integral, because here we just have to prove that the projection of this measure converges to the projection of this measure. And since it's in the sense of integral, it's just a change of variables. It's not hard to obtain. And to finish, I would like to mention two works in progress, joint with Ricardo Rosa and Cecilia Mondaini, which is a PhD student of Ricardo. So he talked about this yesterday, which is the abstract formulation for the construction of statistical solutions of evolution equations, because until now we just have this theory for the Navier-Stokes equations, but it's not, there is not a special with this equation. Actually, we can make this for all the types of equations. And also, we can consider approximation models in this abstract formulation and also obtain the convergence, since now we know how to do this. And of course, one of the application will be the Navier-Stokes alpha model. Actually, these other three here, we already checked, and it works also. Okay, thank you very much.